Hello, students. So today we begin to look at the nervous system. The nervous system, to introduce this, what I like to do is, imagine I take a tennis ball and I throw it to you. Um, your nervous system is involved in developing a response to my action there. And so if you think through what is it that my nervous system has to do in order to catch that tennis ball I'm thrown, there's three kind of components to this. There's a sensory input. First, you have to see that that tennis ball is coming at you. Second, integration. You have to think about what you're going to do. Am I going to catch the ball? Am I going to dodge the ball? Am I going to, bat it out of the air? What am I going to do? And then finally, there's motor output, which means that my nervous system has to send a signal to my muscles that will cause them to kind of bend and move and actually catch that ball. So again, sensory input as I see it, integration as I think about it, motor output as I send signals to my muscles to catch it. This flow chart here is actually going to take us roughly half the course. We're going to begin here with integration and kind of learn about the brain and the nervous system and how that system works. Then we're going to back up and we're going to look at sensory input and understand the sense organs. How do our eyes and ears and nose and mouth, tongue, I should say, detect information from the environment. And then finally, we're going to talk about motor output, the bones and the muscles, and how do they work with the nervous system to generate movement. So kind of mentally remember this little flow chart because this is going to carry us for quite some time now. By way of overview, I just want to introduce kind of the two main divisions of the nervous system. First, we have the central nervous system, which consists of the brain and the spinal cord. I want to highlight the spinal cord is not the bone that you feel on your back. Those are the vertebrae. The spinal cord is actually nervous tissue. It is continuous with the brain, and it's the same material as the brain, which, by the way, is about the texture of like firm tofu, I'm told. So it's kind of one and the same thing as the brain. It just extends down in there, and it goes about halfway down your back right here, and then branches into a whole bunch of different nerves. The peripheral nervous system are all the nerves that lead to and from that central nervous system. So these nerves going to your arms, going to your legs, these are involved in movement and sensing and things like that. And they kind of send information to the central nervous system and bring information out to the bones, to the muscles. And there's something about the way that pose that, I don't know about that, the way he's standing there. And we can kind of visualize the nervous system as a bunch of cells with these little electrical signals kind of zipping around through there. And we're going to look more closely in subsequent screencasts about how things zip around like that. But for now, I just kind of want you to understand this little zipping of signals throughout the body. And a good question would be, how fast do they actually go? And so I do this little activity where I have kids form a circle, and we kind of do the whole classroom in one big circle. And this is great for when there's not a pandemic. And then everyone holds hands, and one kid squeezes the hand of the person next to them. And then that person squeezes the next person's hand, and that person squeezes the next person's hand, and that person squeezes the next. And it just kind of goes around. And then we time how long it takes to go around in a circle. And if you do this, you find that it is an extraordinarily short amount of time that it takes for each person to sense the signal, process the signal, and send information to the muscles to cause motor output. So, again, this kind of helps illustrate that sensory input, processing motor output, and also that idea of these signals kind of zipping up and down through these nerves. So I like to introduce that way. So to begin with the nervous system, the first thing we're going to do is look at the brain. And what follows is a fairly long, list of structures that make up the brain. And we're going to learn how all these pieces and parts work together. So we're going to start with the cerebrum. And the cerebrum is most of what you see in this picture. Pretty much everything up here is cerebrum. This bottom part is not cerebrum, but everything from this line up is cerebrum. So it's huge. So huge that defining it doesn't really make sense because it's just such a vast structure with so many different parts. It makes sense to kind of look at each part individually. So before we do that, though, let's just look at some general features. One, you'll notice that if you compare the human cerebrum with a mouse cerebrum, we got a lot of wrinkles. This is part of what makes humans so gosh darn intelligent, is because that gives us more surface area for thinking and processing and making sense of the world. Mice don't do this because they don't have those wrinkles. There's names for those wrinkles. The gyri are the bumps, the high points, and the sulci are the grooves in between. So if you imagine folding a paper accordion style, the high points would be the gyri, the low points would be the sulci. And then note that the singular form of these terms are gyrus and sulcus. So those names and those folds have those names. The second thing you'll notice about the cerebrum is there's two colors. There's kind of a whitish color and a grayish color. And we have names for those two colors. The whitish color stuff is called white matter, and the grayish color stuff is called gray matter. Thank you, gods of naming. That's very helpful. Why the different color? Well, it turns out that the white matter has an extra layer of fatty insulation around it called myelin. We're going to talk a lot more about myelin later. You can kind of see that this is a neuron entirely in the gray matter. It does not have myelin. Here's a neuron that is in the white matter. It's actually yellow in this diagram, but you can see these kind of sausage-like things around it. That is the myelin. So the myelin gives the white matter the white color. The gray matter lacks the myelin and is therefore gray. And you'll notice the outer layer of the brain is entirely gray matter. That gray matter has a special name. It's called the cerebral cortex. So this is the area that's involved in higher level thinking skills, memory, thoughts, consciousness, that sort of thing. Again, this outer layer of gray matter, the cerebral cortex. And so again, the wrinkles, the gyri and sulci, create more surface area for that material. In fact, there's so much surface area that it's about the size of a pillow. And so again, I've kind of talked about this, but to get it in the skull, all those wrinkles work and help make it fit in there. You'll also notice, if you look at a brain from the top, that there's this long line down the middle. That line is called the longitudinal fissure. And it sort of separates the left and the right halves of the cerebrum. Each of these two halves are called cerebral hemispheres. So it might be worthwhile to take a moment, now that we've gone through that, to kind of review the difference between the gyrus and the sulcus, the white versus the gray matter, the cerebral cortex versus the cerebrum as a whole, and then you don't have to contrast longitudinal fissure with anything, but just what is it. So take a moment, make sure you got those. So now what we're going to do is look at the different regions of the cerebrum. Obviously, the actual brain is not color-coded nicely, but in this diagram, you can see there's kind of four main regions. There's this yellow frontal lobe, the purple parietal lobe, the greenish occipital lobe, and then the bluish temporal lobe. And let's take a look at these. So the frontal lobe, you can think of as the output center. This is the part in the front of your head, and it's sort of what you put out to the world. So your personality is housed there, your morals and ethics, higher order thinking skills, speech. Now you might ask, how do we know things like that? And we've actually learned this from some rather grisly medical cases. A very famous one is someone by the name of Phineas Gage. And Phineas Gage was a railway worker. And when they were building the railroads across the United States, there were rocks and things in the way. And so what they would do is they would drill holes in the rocks, and they would pack explosives into the rocks using this device called a tamping iron, which you just kind of use to like pound the explosive into the rocks. They would, put a fuse in, back up, very important step, blow up the rock and clear the rubble and build the railroad. Well, Phineas Gage was doing this. He was packing some explosives one day, and for some unknown reason, the explosive went off. And that rod actually ended up blasting through his head. It came in under his left eye and went right through his frontal lobe. Now, amazingly, this did not kill him. He went on to live, but it was not exactly a normal life. His personality had been dramatically changed. Whereas before he'd been pretty easygoing, laid back guy, After this experience, he became very rude. He would swear. He'd make inappropriate comments to women and other people, and just kind of became not such a great gem of a human being anymore. And so, from this case and others like it, we kind of realize that that frontal lobe is associated with our personality, and damage to that can actually change your personality. Fun fact: the frontal lobe doesn't fully develop until older than you guys are. And because of that, sometimes high school students, forgive this, just being honest, do not have the best judgment and sometimes make poor choices. um, that frontal lobe is a very important part of our brain. By the way, here's some um, little stats on that tamping iron. And this makes it seem like it lodged into his head, but it actually passed through and landed about 25, 30 feet behind him. Within this frontal lobe, there's another area I want to highlight. It's called the motor area, and its job is to control voluntary muscle movements. And it's at the very back of the frontal lobe, or the posterior side. And again, that should make sense because most motor movement is an output, right? So if I'm doing this, it's an output. What's interesting about this motor area is that specific parts of it control specific parts of the body. So, this part of the brain is responsible for moving the hands and the fingers and the thumb, this part, the lips and things like that. Now you might wonder, why is so much to brain devoted to your hand versus like your hip and your trunk? Your hip and trunk are much larger parts of your body, so why don't they get as much brain? Well, it turns out it's because your hands are so complicated, right? You can do all sorts of things. You can like do this. Woo. You can play the guitar, you can play piano, you can use a screwdriver, you can text, you can old person text, where you do this with your fingers. There's all sorts of things you can do with your hands, and so you need a lot of brain to be able to coordinate all those elaborate, complicated movements. Your hip and trunk, they just kind of walk, they just swing back and forth, and you don't need a lot of brain for that. Here's kind of a fun picture that shows what your body would look like if its size of each body part was proportional to how much motor area was devoted to it. The parietal lobe is next. Think of this as the input center. It integrates sensory information, particularly touch. And there is a similar area to the motor area. This time it's in the parietal lobe, though. And this area is called the somatosensory area. It perceives touch information. And again, certain parts of our body are more sensitive to touch than others. Your hands and fingers are very sensitive because you can do fine coordination and movement through them. So just like before, the sensitivity of the area is proportional to how much brain is devoted to it. Next, we have the temporal lobe. This is involved in processing hearing, which we'll discuss more in our next unit. And then the occipital lobe is in back, and that we'll deal with when we discuss vision. So those are the four major areas: frontal, parietal, occipital and back, and temporal on the sides. But then there's other regions. The corpus callosum is a structure that connects the left and right cerebral hemispheres. So remember, there's that longitudinal fissure, that line that kind of goes down the middle. And if you peel them apart, they're connected down here. That connecting band is the corpus callosum. And if you cut the brain in half and look at it in a sagittal section, this is what it's going to look like. It's this white kind of band right here. That's the corpus callosum. And this allows the right and left halves of the brain to communicate. Now, interestingly, with epilepsy is a condition where you get uncontrollable seizures. And what happens, they found, is that seizures are simply out of control electrical activity. And they found that that sometimes when that electrical activity crosses the corpus callosum, it amplifies. So it kind of amplifies, goes across, amplifies, goes across, amplifies, and it kind of gets out of control until you kind of collapse and have a seizure. So what they found is that by severing the corpus callosum, they can actually treat epilepsy. But that has some consequences, and I think I'm going to pause here and leave that as a cliffhanger for our next screencast. What consequences would come from severing that?